Okay, applications to computer graphics. So, okay, you all know about computer graphics here. Uh, Computer graphics are displayed or animated on a computer are displayed or animated on a computer screen, and computer graphics are widespread and growing rapidly. You know that. Um, Computer-aided design (CAD) is an integral part of many engineering processes, such as aircraft design, and they talk about that in the chapter introduction about aircraft design. How many have heard of computer-aided design in here? How many have heard of that term before? Okay, Olivia has, Samantha, wonderful, wonderful. And Benjamin and Shravani, excellent, excellent. Nifani. So the entertainment industry has made good use of computer graphics, special effects, PlayStation 4, Xbox One. Um, this section is going to examine some of the basics used to manipulate and display graphical images. Okay, so how are we going to use matrices? Let's look at an example. Here's an example one. The capital letter N here in figure N, the capital letter N. It's determined by 8 points, the 8 vertices here, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so you could, how do you store the letter N on a computer? Well, you can have the vertices stored on the letter N, and that would uniquely determine the letter N if you had your, just line segments connect the vertices. So, but of course, the vertices, you have to store the information. How do you store the information? You store it in a matrix. You store it in a matrix. And here matrix D stores the vertices. Okay, are there any questions on that idea? All right, well, maybe we want to do something with the N. Okay, maybe we want to do something with the N. Okay, maybe, for instance, we want to do a shear transformation. Remember the problem? Remember the example where we had the sheep get sheared? Well, we can do the same thing with N. Whoops, hold on. Let me get my book back. One moment. One moment, everybody. The book just seems to go out and in from time to time. All right, hang on one moment. Okay, so once again, here's this letter N. Okay, hold on. I want to make this a little bit bigger. Okay, here's this letter N, and you store the vertices of the letter N are coordinates, and you store the coordinates in a matrix D. Okay, so now what you can do, right, is you can cause the matrix N, you can do a transformation on the matrix N. So like, for instance, if you were to, and hold on, I got to go back for a minute. Yeah, well, this matrix A in example 2 is, let's see, are you seeing this book? Are you seeing this? Hold on. Let me go out and come back in with the book. Sorry. Let me go out and come back in. Sorry for the delay, everybody. Just gotta. Okay, let me get in here. Okay, so did you see the example here? Example 1. I mean, I know the screen the book kind of went out on us, but did you all see that? All right, good, good. So you see the letter N, you can store the coordinates of the vertices of that letter N. Thank you, Shravani. And there you go. So, okay, that's great. But we want to see some activity. Animation has movement. We want to see some activity. So what if we were to cause that matrix N to bend, like you're seeing, to slant, like you see here in figure 2. So in figure 1, the letter N is upright, vertical. But in figure 2, we want to slant the N. So that's doing activity on the N. Well, the way you do that is a transformation. You have to do a shear transformation. The matrix A here, 1, 0.25, 0, and 0.1, you can take A and multiply it by D, and it's going to do a shear transformation. Okay, it does a shear transformation. So that's the effect. That's the effect of multiplying A by the matrix D. And you see, you can do animation through these through matrix multiplication. Is everybody seeing this okay on the screen? Everybody's good? Okay, good, excellent, excellent. All right, so, all right, but you can do additional things, okay? You can do additional things. Like, for instance, in example 3, they talk about compute the matrix of the transformation that performs a shear transformation first, and then scales all coordinates by a factor of all x coordinates by a factor of 0.75. So you see this matrix S, when you multiply the matrix S, the 0.75 in this upper left-hand corner with the matrix multiplication, what does it do to does it affect the x coordinates or does it affect the y coordinates? That 0.7. It affects the x coordinates. That's right. That's right. The y coordinates are left alone. So the effect is, if you want to perform a shear transformation on the letter N and follow it by a 25% shrinking with regard to the x coordinates, okay, you would first multiply that matrix D in example 2 by the shear transformation, because order is important, and then you would multiply that product matrix by the scaling. And together then, this matrix, well, this matrix, called a composite matrix, does the shearing of the letter N and the scaling down by 25% in the x direction of the letter N. It does that all in one step. And so the composite transformation would produce this N. You compare figure 2 and figure 3. Figure 2 is the slanted N. Figure 3 is the slanted N, but then you're scaling it. It's thinner in the x direction. All right, are you okay? Are there any questions on that? Okay, well, who's feeling good so far? Who's feeling good so far? Who's feeling good? Okay, good. I just yeah, turned off my email. I don't want that to, you know, I'm focused on you. I don't want any distractions here. All right, so well, let's continue on. Let's continue on. So now we're going to talk about something called homogeneous coordinates. So I want to say this the right way. I want to say this the right way. So up to now, when you had you work in the XY plane, you have a coordinate in the XY plane, and you want to do a transformation on the coordinate. What you've done is you've multiplied that coordinate by some 2x2 matrix, right? Some 2x2 matrix. Maybe the matrix does a rotation. Maybe the matrix does a reflection about the x-axis or the y-axis. But what haven't you seen before? You have not seen a translation yet of a coordinate. You've not seen a coordinate get moved up, or, you know, like, you've not seen it get moved up and then down. Like, for instance, here you have something called a translation of 4x3. So you have this red triangle. You have this red triangle, and what you want to do is you want to move it 4 units to the right and then 3 units up. Well, to do a translation, you can't do that with a 2x2 matrix. You need to have a 3x3 matrix to do a translation. Okay, and therefore you need to think of your XY coordinate as a homogeneous coordinate that has three elements to it. 3 elements to it. It would have an X in the first spot, a Y, hold on, an X in the first spot, a Y in the second spot, which you're used to, but then you need a 1 in the third, as a third component. The 1, what it does is it allows you to model translations. So if you look at example 4 here, let's say you want to take a coordinate xy and you want to translate that to a new position, x plus h coordinate y plus coordinate x plus h comma y plus h. In order to do that, x gets transformed into x plus h, y gets transformed into y plus k. But to do that, you see in example 4 why you need a 3x3 matrix. You need like the 3x3 matrix has a 1 in the bottom right hand corner. Do you see why you need the 1 there? Do you see why you need the 1 there in the bottom right hand corner when you do the matrix multiplication in order to translate an xy coordinate to a new coordinate x plus h, y plus k? Okay, thank you, Eleanor. You see, you need the 1 there. I mean, there would just be no way to do the translation of a coordinate to another coordinate without a 3x3 matrix. And if you have a 3x3 matrix, you got to multiply it by a 3x1 vector. So the coordinate xy is represented as the vector xy1. Okay, so far so good. If you think back to like section 1.9, when, and you know, well, you had some in 1.8, but in section 1.9 you learned about shearing, you know, shearing, contractions, expansions, reflections, all of those types of matrix transformations that act on coordinates can be done using a 2x2 matrix, but you need a 3x3 matrix if you want to actually do a translation. So, okay, well then what we're going to do is, in example 5, they give some examples where, you know, like things you've seen before, okay? Like the first matrix has a rotation. The second matrix, the top, if you just focus on the, just on the top left-hand corner, that matrix has the 0, 1, 1, 0. That'll do a reflection. The third matrix, if you want to scale x by s and scale your y coordinate by t, that would be just the highlighted 2x2 matrix that you see there. And normally, back in section 1.9, you would have 2x2 matrices with those, with like those. You'd have 2x2 matrices that look just like what you see in the yellow there, in example 5, in the yellow that I've highlighted. Let me get this off here. Hold on. How many does it ring a bell? How many of you does it ring a bell? These, what I'm highlighting in yellow, those elements in the first matrix in yellow would do a rotation. Second matrix, you'd have a reflection. Good, Benjamin. Good, Ariana. Good, Abby. And then but now what you're doing, because you want to include transfer, you want to also now transform points in the XY plane. You need to have a 3x3 matrix where you have a 1 in the bottom right-hand corner. You see each one, there's a 1 in the bottom. Well, I didn't want to do all that, but you know what I mean. There's a 1 in the bottom right-hand corner. And then zeros on the rim. Okay, and then your homogeneous coordinate would be x, y, and 1. So let's look, it seems like you're comfortable with this. Let's look at a composite transformation here. Okay, so here in example 6, they want you to find the 3x3 matrix that corresponds to the composite transformation of scaling by 0.3. If you scale by 0.3, what percent are you reducing? I got to be a little careful here. I think I might have said, if you scale by 0.3, what percent are you shrinking your triangle? If you scale, I mean, look on the left there. You have a little picture there. If you scale coordinates by 0.3, let me see. There was a response there. 70%. 70%. Yeah, Nafani, it would be 70%. That would be the amount that you shrink. Would be 70%, because it's like taking the coordinate and multiplying it by 30%. You're only going to get 30% of the coordinate. Well, I got to be a little bit careful, but Nafani, are you okay with that? Okay, all right, you're feeling it. Okay, all right, good. So now, okay, we're going to do a scaling of 0.3. That comes first. Okay, we're going to do 3. This composite transformation is going to consist of 3 things. So first we got to do the scaling, okay? And you're doing it on your XY coordinate, but it's a homogeneous coordinate. You got to have the 1 down there. Then after you do the scaling, you're going to do a rotation of 90, whoops, hold on. After the scaling, you're going to do a rotation of 90 degrees. Okay, well, here's the rotation. Let me just try to, hold on here, class. Let me just try to, I'll do it piece by piece. Okay, there's your scaling. Here's your rotation. And I like to use, to find out my matrices, I like to use that theorem from section 1.8, or no, the theorem from section 1.9, where you transform your E1 and E2 vectors, into the new vectors, and then you get your matrix out of that, because it always works. Okay, and then finally, you're going to have a translation that adds negative 0.52 to each point, and so there's the last one, and you see there the negative 0.5 and the 2. You see where they go. They go right there. Let me see. I think I might have heard a chat here. Are there any questions? Are there any questions? Okay. Well, now, if you want to do this this composite transformation, let's see. Nafani, rotation is he's asking about the second step there. Hold on. Is it rotating 90 degrees counterclockwise? Well, let me see here. One moment. So 1, 0 gets moved to 0, 1, and 0, 1 gets moved to negative 1, 0. Yes, that's 90 degrees counterclockwise. Yep, that's right. All right, and so now, what would the effect be of multiplying the three matrices together? What would the effect be? Well, first of all, this would be the matrix you need. This matrix here, let me just get this off. By multiplying the three transformation matrices, you end up with this matrix here. First row is 0, negative 0.3, negative 0.5. Second row is 0.302. Last row is 0, 0, 1. Okay, and the effect, let me see, let's see, did we lose the book? Hold on, are we losing the book here? Hold on. One moment, let me. Okay, let me see, are we back with the book? Yes, okay. So the effect then of this composite transformation is what you see right here. The last step was the translation. So hold on, I don't know why that. Sorry, class. Let me get this off. I do not want email interrupting our lesson here. How many of you noticed sometimes you might accidentally have email open twice, like your MC email open 2 times and you didn't know it? Has anybody ever? That's what happened to me. I don't know if that's ever happened to you, but at any rate, here we go. So so do you see what's going on here? You see how through this matrix that takes the original figure, scales it, rotates it, and translates it. And so if we were to program that matrix into a computer, and it would act on an object, and an object would, or act on the letter N or whatever, and the letter N's represented by, a bunch of coordinates. Well, the triangle would be represented. We would have a matrix that represents the triangle. If you multiply that triangle matrix, the matrix that represents the coordinates of the triangle, if you multiplied it by this matrix here, 0, negative 0.3, negative 0.5, 0.302, 001. That's going to be your new result. And that's how you get animation. That's how you get animation. How many think that's pretty cool? Okay, Olivia likes it. Nafani likes it. Lewis likes it. All right, I'm getting a lot of positive responses. I agree, Shivani. Yeah, and back, like, for instance, I don't know if you've ever seen the movie like Snow White or Bambi, these movies that go like back 80 years, 70 years. Okay, if you look at those movies, yeah, they were awesome. But of course, they're awesome. But of course, the animation was done differently. Um, I mean, they didn't have computers to do the animation. Okay, they didn't have, like, I mean, we have very powerful computers today, and think about the animation. Well, even think back to think about video games. How many maybe have heard of Pac-Man, the video game Pac-Man, or Space Invaders? Okay, Abby knows what I'm talking about. Space Invaders, Defender, Pac-Man. Gosh, I'm trying to think of some old video games. Are there others? How many have heard of Dig Dug? Dig Dug? Maybe you could throw out a few old video games. So Shirvani has it on his phone. Pong. Okay, Justin, there we go. Pong. Okay, well, those games, when they were made, they were run by computers, but now computer processing is much quicker, and so we can have huge matrices, where we can have a lot of matrices, right, to do a lot of really good animation. And every time you do animation, you're multiplying matrices together. But to multiply matrices together takes computing power, and we have very good computing power now. So, like, we have 3D graphics. Those games, Pong, Pac-Man, those are 2D graphics, right? Those are two-dimensional. Now we have three-dimensional graphics. Okay, so what's like a three-dimensional? What's a three-dimensional video game? Like Fortnite. I've heard of Fortnite. That's three-dimensional? What are some other three-dimensional, like, popular video games that maybe people play? Does anybody? Call of Duty? Okay, Call of Duty. And all right. Well, let's see. Thank you, Marvelous. Hung says CSGO. I'm not sure I know that one. PUBG. Okay, so I'm going to have to get up to date on these video games, but compare the animation, the graphics on those video games compared to the animation, the graphics back, 30, 40 years ago. And it's just really cool. So this is computer graphics, and we're going to talk in next class. You've seen now how two-dimensional graphics works, but we want to do three-dimensional graphics as well. And so when we meet on Monday's class, I'll do an example where we do three-dimensional graphics. All right. So I think we're. Are there any questions before I stop the recording? Okay, I will stop the recording.